All right, on to learning objective 5. We're going to describe how adenosine triphosphate, or ATP, acts as an energy currency for cells. So ATP is the source of power, or the batteries for cells. It can do cellular work by what we call energy coupling. So ATP can release its third phosphate group, because it's triphosphate, 1, 2, 3 phosphates, and that releases a lot of energy. So that is a strongly exergonic reaction, and it's so strong that it can make endergonic reactions overall exergonic. So a cell is doing three main kinds of work. Chemical work, making new molecules by making and breaking bonds, moving things around, transport, and mechanical work, like your eyeballs moving across the screen, your ears listening to things, um, your muscles moving. That's different types of work. So energy coupling means that we're using an exergonic process to drive an endergonic process. And ATP does that. So how does that work? So here's sort of a model or a cartoon of ATP. As you can see, it's adenosine triphosphate. It is a nucleotide. So here's adenine, represented up here. Here is ribose, a 5-carbon sugar. Here's a phosphate, 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 ATP. Now, when that third phosphate group is broken off, cleaved off, hydrolyzed off, we have a phosphate group, we have ADP, or adenosine diphosphate, because now we only have 2 phosphate groups, and we release a lot of energy, very strong negative delta G. Okay, so how does it work? How does this energy coupling work? Well, in our bodies, we can make our own glutamic acid, which is one type of amino acid, but we also have glutamine, which is another type of amino acid. And how do we make glutamine? We add ammonia to it. So that turns glutamic acid, depicted here as this green triangle, we can make that into glutamine. But we can see the delta G, that requires energy, that absorbs energy, 3.4 kilocalories per mole. So that's just a way of measuring the Gibbs free energy. But the fact that it's positive means it's going to absorb energy. This is not a spontaneous process. So how do our cells do it? Okay, so instead of just doing it all on its own like this and sort of pushing the system uphill, glutamic acid can absorb the energy by hydrolyzing ATP. We put that phosphate group on to glutamic acid. We release ADP, and then we add the ammonia in, and we get glutamine. So how does this work? It works in this way. The delta G, or the release of energy from ATP hydrolysis, is negative 7.3 kilocalories per mole. So it's very strong release of energy. So it's so strong that even though this reaction on its own has a delta G of positive 3.4, it's going uphill. When we release negative 7.3 kilocalories per mole by hydrolyzing ATP, it means that our net change in free energy is negative 3.9 kilocalories per mole. So our delta G net is still negative. All right, so this is probably just like, you're probably like, what is going on here? And you're not alone in this feeling. So let me give you an analogy, something you probably understand after this slide. So ATP drives endergonic reactions by phosphorylating, transferring that phosphate group to another molecule, making a phosphorylated intermediate. Now that phosphorylated intermediate has more free energy because it's got that phosphate group on there. It's kind of, that phosphate group is kind of like a jet engine that gives that molecule energy. So energy from breaking down energy releasing processes goes into making ATP, and that ATP can be used to drive endergonic or energy consuming processes. And then we can recycle the ADP and the phosphate groups to keep this going. All right, so here's that analogy I promised you in the form of money. We understand how money works, right? You need to have some money to do things. If you are in debt, it's very hard to do any work, and you need to get out of debt. So let's say that you have a company that is a phone making company, and you make iPhones, which are very profitable, and you also make old-timey rotary landline phones, which are not very profitable. But you absolutely have to keep making these landline phones. Okay, so the landline phone is analogous to the glutamine in the previous example. But in order to keep your company working, you have to make a profit. You have to have a net profit. So for some reason, maybe you've got a government contract that says they need landline phones. You have to keep making the landline phones, but you also have to keep your business afloat. So what do? You make the landline phones, but you have to keep making the iPhones as well. The iPhone is kind of like ATP. It's making you $7.3 billion, even though you're losing $3.4 billion in this government contract that you're locked into, making these glutamine rotary phones. So as long as you keep producing the iPhone, you still have the capital to continue to produce those landline phones, and you're still making a profit of $3.9 billion. That is how energy coupling works. So in order to make something that absorbs energy, we have to have another process that releases more energy than the energy consuming process. Which means, so instead of billions of dollars here, think kilocalories per mole. And instead of these positives, which would be profits, think negative delta G. And hopefully you can see how this energy coupling process works. All right, learning objective 6, we're going to talk about oxidation and reduction reactions, which are types of chemical reactions, and what happens when oxidation and reduction are occurring. So, when we start talking about cellular respiration in the next chapter, what we're going to find is this is a way for us to produce ATP. And hopefully now you appreciate how important ATP is. But in order to produce ATP, we need to do a lot of energy transformations. And the power for making new ATP ultimately comes from electrons. So remember, chemical reactions are making and breaking of bonds. Making and breaking of bonds is, in turn, interactions between the electrons in atoms. So we can transfer electrons to release the energy that is stored in chemical bonds, and we can use that to produce ATP. So, redox is what we call oxidation reduction reactions, because it's reduction, oxidation. When we transfer electrons between reactants, that is an oxidation reduction reaction or a redox reaction. So, if a substance is oxidized, it is losing electrons. If it is reduced, it is gaining electrons. So what's being reduced is the amount of positive charge. So you're going from a strong positive to a less positive or a negative number. Or the mnemonic device that I like is oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. So let's look at sodium chloride, table salt. When we form an ionic bond between sodium and chlorine to produce table salt, which isn't where table salt comes from, but let's say for the purposes of this that that's what's going on. That sodium atom loses an electron to fill its valence shell, because it just has one in its valence shell. It loses it, and that's got that next layer of electrons. It's totally full, which makes it happy or stable. Chlorine has 7 valence electrons. It picks up that extra electron from sodium. It has 8 in its valence shell, and it is happy and stable. So sodium loses an electron, so it's becoming oxidized. Chlorine is gaining an electron. It is becoming reduced, going from neutral to negative. And so this is an example of a redox reaction. So you can generalize and say that if we have molecule X and atom Y, if we move an electron from X to Y, one of these reactants is going to become oxidized because it's lost an electron, and one of the other reactant is going to gain that electron and become reduced. So we call them redox reactions because you can't have one without the other. Remember, we can't create or destroy energy. We can't create or destroy matter. So if an electron is moving, it doesn't just go into nothingness. It goes from one molecule to another. If I give $1 to you, then I'm less $1 and you are greater $1. So when we burn things like methane gas, we can burn in the presence of oxygen, and what happens to the carbon in methane is it's going to become oxidized. So the carbon that's in methane, remember the carbon and hydrogen, hydrocarbons are very good at sharing electrons. So the electrons are kind of going back and forth equally between carbon and hydrogen. And an oxygen gas, remember oxygen loves electrons, but if you have 2 oxygen atoms together, they have to share those electrons very evenly because they're both equally greedy for those electrons. Okay, so we burn the methane in the presence of oxygen. What happens to that carbon? All right, now carbon is connected to 2 oxygen atoms. And what happens to it? Well, now those oxygen atoms are like, hey, now I'm sharing with carbon, and carbon's kind of a wimp for electron density. Carbon's not going to be able to pull those electrons away. So these oxygen atoms are like, yay, I get to keep these electrons more often than carbon does. And the carbon's like, I just got kind of screwed out of my electrons. And we release energy. And we also get water out of this. And again, those hydrogens that were on methane, they were sharing very nicely with carbon. Suddenly they're like, hey, I've been screwed out of my electrons again, and I'm in here with water. And that oxygen atom's like, hey, cool. I get to hold on to these electrons, and those hydrogens can't pull them away from me. So the system has more stability because they don't have this equal sharing of electrons that you see in methane or in oxygen. But now oxygen is pulling electrons away from carbon. Oxygen is pulling electrons away from hydrogen. So even though we don't have full charges that are forming, we do get these partial charges, and the electron density, or how much time the electrons are spending around one atom versus the other, has changed. And this is what we're going to see when we talk about cellular respiration.